Hi, we're the Washington College Electric Boat Team, and this is our mid-year presentation to the American Society of Naval Engineers for the Promoting Electric Propulsion Collegiate Competition.
With the new changes in rules limiting systems to 55 volts nominal, our previous two boats are not legal to race at PEP. After a lot of discussion, we've decided on a 2-year phased approach to preparing our new competition boats. With maximum efficiency in mind, we would like to incorporate hydrofoils, but since we don't have experience building foils or designing the control systems that maintain stable flight, we are planning a 2-year build for the foiling boat, which will use a displacement catamaran hull.
The boat we have focused on for the 2025 race season will be the playing hull, which is something we are familiar with and can achieve high speeds with. With the desire to fit our entire boat within a 12-foot cargo trailer, we chose an 11.5-foot hydroplane hull to build from.
Initially, we wanted to use a Dutch-built motor that incorporated the motor controller and the mounting in one unit. Due to the delays in shipping, we were forced to abandon this option.
For maximum efficiency, we want to avoid using unnecessary gearboxes. Most gas outboard engines run at 5,000 to 6,000 RPM, and the selection of powerful 48-volt motors that spin fast is limited. We opted for the ME1616 motor that can produce 45 Newton meters of torque, spinning at 3,600 RPM, with 48 volts and 250 amps of power. With that slower RPM, it's less ideal to couple an outboard motor with a 2-to-1 gear ratio in the lower unit. So we chose a straight shaft with a motor and prop, from a motor to a prop.
Using an online prop calculator, we determined that the ideal 3-bladed prop would be at about 8.4 inches diameter at 12.9 inch pitch. We plan to look for props in that range and perhaps adjust from there depending on the boat's performance. We purchased our wood hydroplane already partially built, although the outer shell of the hull was epoxied together, and we first need to take a step back by removing the inadequate fiberglass tape from the seams before we could finish fairing the wood and then reinforcing the hull with a 9-ounce layer of fiberglass. While we were at it, we added a tow point to make it compliant with PEP rules. After a few weeks of glassing and fairing the hull, we installed a watertight hatch forward of the cockpit in order to have access to the back side of our dashboard for routing control and power cables.
Just before the end of the fall semester, we took the hull out for a speed test with a dummy load of 160 pounds of cement and powered it with a 9.8 horsepower, 7.2 kilowatt gas outboard motor. We did this to get a general sense of how the hull would perform with a known power source before taking the time to design and build a custom electric drivetrain. As we continue forward, we plan to install a shaft log to pass the shaft through the hull from the motor to the propeller. We will have to build a custom motor mount and add a thrust bearing to take the load off the propeller.
Next, we need to design and build a 3D printed rudder, which will then wrap in fiberglass. We built a custom cable pulley to route steering cables to the transom.
A watertight compartment needs to be created for the batteries, allowing us to isolate them from the motor in case water leaks in around the shaft seal. We will build a dashboard with a throttle control, power instrumentation, GPS speed, a kill switch, and any other controls needed during the race.
As we navigate through the design, build, and revision process, there are risks that we recognize. Although we wanted to bring a hydrofoil to this year's competition, we thought it would be risky to build the boat, design and build the propulsion system, and design, build, and troubleshoot the hydrofoiling system. If funding allows and we can purchase the necessary components, we plan to bring the second boat, the displacement catamaran, with a partially built propulsion system, but without the foiling components. For our hydroplane, we thought it would be a risk to hold out for one of the higher-end motors available from the Netherlands or Germany. If we waited for them to arrive, there was a good chance our planing boat would not be ready for the race.
Weight is a huge consideration in this 11.5-foot hull that is smaller than we are used to. Rather than using larger prismatic lithium iron phosphate cells as we have in the past, we are opting for smaller cylindrical lithium ion cells. Although these will only have a fraction of the cycle lifespan compared to lithium iron phosphate, for their size, they can deliver much higher current, making them more ideal for a boat designed to race top speed for a shorter distance. We need to keep in mind the increased risk of this battery chemistry and design redundant monitoring systems for battery temperatures.
We are keeping in mind that a drive-by-wire servo-controlled steering system might be less responsive compared to a standard mechanical steering cable. Although we need to be able to drive by wire when unmanned, we plan to disconnect the servo to allow for manual steering when the boat is manned, using a cable-driven mechanism we've begun fabricating.
Hydroplane hulls are not well suited to rough conditions, a contrast from our previous hulls. We need to be prepared for any conditions in which a race might be held. To make the boat safer in choppier conditions, we have designed and plan to install a windshield that will help deflect spray and keep the cockpit dry. Our watertight battery engine compartments will both keep those systems dry and provide flotation in the event of a wave breaking into the cockpit.
We plan to fill the sponsons with 2-part expanding foam to make the boat unsinkable and at the same time add more rigidity to those planing surfaces.
We want to thank the American Society of Naval Engineers for this opportunity to explore these innovative technologies through PEP. We'll see you all in Virginia Beach in April.